What if we could build brand new materials, atom by atom, specifically designed to solve some of the biggest problems we face? Well, today we're going to dive into a molecular architecture so revolutionary, it's already shaping the 21st century. Just for a second, imagine a material that could literally pull fresh, clean drinking water right out of the driest desert air. Or picture one that acts like a super sponge for pollution, grabbing carbon dioxide as it comes out of a factory smokestack. I know, it sounds like something straight out of science fiction, but that's exactly what we're talking about today. And this incredible potential is exactly why the Royal Swedish Academy of Sciences has awarded the 2025 Nobel Prize in Chemistry to three absolute pioneers: Susumu Kitagawa, Richard Robson, and Omar M. Yaghi. Together, they created a completely new class of materials, something called metal organic frameworks, or as we'll be calling them, MOFs.
But to really get why MOFs are such a massive game changer, we have to rewind the clock a bit, back to a time when building with molecules was, let's just say, more of an art than a science.
You see, before the 1990s, chemists were wizards. They were amazing at making individual, really complex molecules. But, as Nobel laureate Roald Hoffmann famously put it, when you tried to build bigger, predictable structures in 3 dimensions, well, chemistry was a synthetic wasteland.
I mean, think about that. Even for the simplest crystals, chemists couldn't reliably predict how the atoms were going to arrange themselves. In 1988, the editor of the journal Nature actually called this a continuing scandal. It was mostly just guesswork, a lot of trial and error, a far cry from the kind of precise engineering that chemists were dreaming of.
So how in the world did we find our way out of this wasteland? Well, that's where our first pioneer, Richard Robson, comes into the picture with this brilliant flash of insight. And the story here is just fantastic. Robson was getting ready for a chemistry class, and he was playing around with those old-school wooden ball and stick models of atoms. And as he's putting them together, it hits him. The position of the holes for the sticks is what dictates the final shape. And that gave him an idea. What if he could use the natural geometry of atoms to link whole molecules together into a much bigger structure?
He took his inspiration from a diamond, right, where every single carbon atom is bonded super tightly to 4 others. And he thought, okay, what if we could copy that structure but just blow it up to a much larger scale? So instead of using single atoms, he used metal ions as the corners. And instead of simple bonds, he used these long, 4-armed organic molecules as the struts connecting them. The goal was to build this kind of molecular scaffolding, something that looked like a diamond, but with these huge open spaces on the inside.
And in 1989, it worked. He did it. He created a predictable, crystalline 3D structure that had these massive internal cavities. This proved, for the very first time, that this kind of rational, deliberate design was actually possible. It was a huge achievement. But, and this is a big but, there was a problem. The structures were really fragile. They were kind of rickety, and they had a nasty habit of collapsing, which, you can imagine, really limited what you could do with them. So the vision was there, but the foundation was pretty shaky. And that's when our next 2 laureates, Susumu Kitagawa and Omar Yaghi, stepped in to build something that was truly meant to last. Let's start over in Japan with Susumu Kitagawa. This is a guy whose whole guiding philosophy was to find the usefulness of useless. He loved to chase ideas that everybody else dismissed. In fact, he faced constant rejection from funders who told him that his early materials were totally unstable and had no purpose. But he just kept going, and in 1997, he had a massive breakthrough. He created the very first stable MOFs. These were frameworks that you could empty out, and then they could absorb and release other molecules like gases over and over again, all without falling apart. This was the critical step forward the field had been desperately waiting for.
Kitagawa also had another really key insight. He realized these materials didn't have to be totally rigid. He imagined what he called soft porous crystals, or 3rd-generation frameworks. These were dynamic structures that could literally change their shape when a gas molecule came in or went out, almost like a tiny pair of molecular lungs breathing in and out. It was a brilliant concept.
Okay, now let's shift our focus over to the US and to Omar Yaghi, the person who would take these frameworks and build them on a scale that was just breathtaking.
So it was actually Omar Yaghi who, in a 1995 paper, officially gave this whole field its name, Metal Organic Framework, or MOF. His ultimate dream was to totally transform chemistry, to make it more like building with Lego. You know, a process of rational design where you could pick your pieces and build literally any structure you could possibly imagine.
And in 1999, his group unveiled what has basically become the icon of the entire field, MOF5.
This thing was the complete package. It was unbelievably stable. You could heat it to 300 degrees Celsius and it wouldn't collapse. And the amount of space on the inside, it was truly mind-boggling.
So just how spacious are we talking? Well, the internal surface area was measured at 2,900 square meters per gram.
Okay, so what on earth does that number even mean? Well, to put it into perspective, that is the entire surface area of a football pitch, folded up and packed into just a few grams of powder that could fit on a teaspoon. Yeah, a truly staggering amount of room on a molecular scale.
Yaghi then formalized this whole approach into a concept he called reticular synthesis. You can think of it as the ultimate instruction manual for building molecules. It gave chemists a clear, reliable method for choosing their building blocks to assemble specific, ordered structures with perfectly tailored properties. The Lego kit had arrived.
So, with the foundational work of Robson, Kitagawa, and Yaghi all in place, the floodgates just burst open. Chemists finally had the toolkit they had been dreaming of for decades, a way to design brand new materials from the ground up to solve our biggest global challenges.
And this is just a tiny, tiny sample of the tens of thousands of MOFs that now exist. But just look at what they can do. MOF 303, harvesting drinking water from the air. CAF20, being tested to capture CO2. Others can soak up those toxic forever chemicals from our water, or even provide a safer way to store hydrogen fuel. I mean, the range of solutions here is just incredible.
It's really an astonishing journey when you think about it. In just a few decades, we've gone from that synthetic wasteland to a cornerstone of modern material science. And this isn't just some academic curiosity anymore. Companies all over the world are working right now to commercialize these materials for real-world use.
And that leaves us with one final, powerful thought. With their almost limitless potential, these metal organic frameworks aren't just a Nobel-winning discovery. They might just be the material that defines the 21st century, giving us the tools we need to build a cleaner, safer, and more sustainable future.